Okay, in this section we are going to be graphing the log function, and so we're going to be learning about that. Before we start though, on our bell work, I just kind of wanted to highlight the difference between these vocabulary words. So the difference between growth factor versus percentage rate of growth. So those don't mean the same thing. Growth factor is actually what B equals. So like on question number 1, it says tell whether the function is an exponential growth or an exponential decay, and then find the constant percentage rate of growth or decay. Well, on this one right here, this is your growth factor. Your growth factor, that's what the B value is. The growth factor is 0.9968, but the percentage, and this one is a decay because it's less than 1. B is less than 1, so this is a decay. Um, so the percentage rate of decay, so that is going to be what the difference is between your growth factor and 1. So since my growth factor is 0.9968, I would say it's 0.9968 subtract 1, and that's going to leave you with a negative 0.0032. Change that to a percent, so move your decimal 2 places to the right, and you get a decrease or a decay, a negative 0.32%. So it's a decay by 0.32%. So that's the difference between the vocabulary words. So down here on number 2, where it says f of x equals 4.3 times 1.018 raised to the t power, well, b is 1.018. That's what b is. So the growth factor is the 1.018. But the percent, since this is a growth, but the percent of growth, to figure that out, you'll just take your 1.018 subtract 1, and that's going to leave you with 0.018. Change that to a decimal, so 2 places, so it's 1.8%. That's your percentage rate of growth. That's your rate of growth. Okay, so difference between those two vocabulary words, and this was 0.32%. That was our rate of decay. And you don't have to put the negative sign out in front, just that's our percentage of decay. Okay, so vocabulary, there's a difference between the word growth factor versus percentage rate of growth. Okay, so here's a picture of the logarithm function. There's some things to notice about the logarithm function. It has a vertical asymptote along the y-axis, so that's its limit. It crosses the x-axis at 1, 0. Just like the exponential crossed at 0, 1, this one crosses at 1, 0. And then you have your rate of change here. It just kind of follows that vertical asymptote, and then we're just kind of slowly increasing. It's not super fast, but it is increasing. So that's the shape. Now, when you type that in your calculator, you may get something that looks like this. Like it looks like your graph stops, and then you get something that looks like this. Okay, your graph does not stop. Notice I put an arrow on the end of mine. Your calculator just can't graph anymore because it's getting so close to the y-axis. Remember, the y-axis is its asymptote. It's continuing on, so you need to know that. So make sure you put your arrows to show that, nope, I know that it doesn't stop right there just because that's what it looks like on my calculator. You need to show that you understand the properties of the logarithmic graph. Okay, so here we're going to graph an exponential, and then we're going to graph this other exponential over here on the right that's kind of written weird. So 2 to the x, we'll just do, we'll do some 0, 1, 2, 3 first. So if I put 0 in, I get 1 out. If I put 1 in, I get 2 out. If I put 2 in, I get 4 out. If I put 3 in, I get 8 out. And then if I put negative 1 in, I get a half out. If I put negative 2 in, I get a fourth. And if I put negative 3 in, I get 1/8. All right, so we'll just graph that exponential. Okay, and it's getting closer and closer here, so it looks like this. Okay, there we go. Now notice on the right here, what I did was I switched my variables. I switched the x and the y. The x and the y. I switched them, and now I want to graph this graph. Well, this is a little weird because we don't normally graph x equals. It normally is y equals because our input variable is supposed to be our x, and then we figure out what the y is. So this one's a little bit weird. So just to make it easier to graph though, instead of picking the x's first, I am actually going to pick the y's first. So because that's my exponent spot, and it will be easier to figure out what x is if I pick the y's first. And we're doing this just to illustrate a point. So I'll pick my y's just like I did over there on the other side. If I put a 0 in for y, then that means x is 1. If I put a 1 in for y, x is 2. If I put a 2 in for y, x is 4. If I put a 3 in for y, x is 8. If I put a negative 1 in for y, x is a half. Negative 2, it would be 1/4, and negative 3 would be 1/8. So notice there's a relationship here between those two. When we come over here and graph them, 1, 0, and 2, 1, 4, 2, 8, 3, and then 1/2, negative 1. You can see it's getting closer. So here we go. So you can see this looks like the logarithm function. So this is a log from the slide that we had before, the previous slide. And this is an exponential. Those two are inverses of each other. So what happens when they're inverses of each other? Well, remember when we're solving algebraically for inverses, we switch the x's and the y's, and that's what I did on the right-hand side. I just switched the x letter and the y letter. I didn't solve for anything though, I just switched the letters. You can see from our table that when we do that, the x and the y values switch, the domain and the range switch. So we got the graph on the left-hand side here, that's our exponential. We got the graph on the right-hand side, which is our logarithm function. If we put in the diagonal line y equals x, which is a property of inverses, remember, then I bet that function would graph over to be that. If I superimpose them on the same graph, you could see that they actually are reflections over the line y equals x. They're inverses of each other. Okay, so that's what this slide is showing us. They're inverses of each other. So the one on the left is the exponential. It's a growth, and you can see its inverse there is the logarithm. And then the one on the right is an exponential decay, and you can see its inverse is also a logarithm. Notice some key things to pay attention to is in the exponential, that key point is 0, 1. In the logarithm, it's 1, 0. See, exponential 0, 1, logarithm 1, 0. If they cross each other, if the two graphs cross each other, remember they'll always cross right there on the diagonal y equals x. The one on the left doesn't intersect each other, so there's no points of intersection there. So down below, we kind of just already talked about this. This says a quick review. How do you solve for an inverse? Remember what I said earlier. If we were going to solve, we would switch the x and the y, and then I would resolve it. So here we go. We got x equals 3y plus 5. Resolve it for the letter y. Then divide by 3. So y equals 1/3 x minus 5/3, dividing them both by 3. So that's our inverse. Well, the problem is when we do the inverse of an exponential, let's go back to this slide right here. We don't know how to do the algebra on this. How do I make that y equals like I did right here? This was easy to make y equals. I just move the 5 over, divide by 3. That's where the logarithm comes into play. Okay, so if they're inverses of each other, this is how it works. This b is always your base right here. If it's in the other format, it's always your base. So basically, if I want to take this, let me rephrase that. So if I want to take the equation on the left, which is the exponential, and I want to rewrite it doing its inverse, this would be the first step right here, b to the y equals x. I switch my x's and my y's. But then to finish it, to make it y equals, we're going to write it as a logarithm. So basically what you say is, I'm going to start here with this. I'm going to start with the power, y equals log, and this base right here is still the base, so log base b of, and then whatever's left over here, that's how we would solve that. That's how you would change that to that, okay? So what we're saying here is to go from an exponential to a logarithm, since they're inverses, we're not going to do the whole switch the x, switch the y, then solve. We're just going to do it in one step. We are going to just rewrite it as a logarithm. That's how you can solve those. If you've got an exponential and you need to have it in a different format, you just rewrite it as a logarithm. So basically a logarithm is an exponent. That's usually what happens. That is an exponent. Look right here. Here we go. See this? That is an exponent. Okay. So these pictures right here just kind of show you what we had already talked about. Original, logarithm, inverses of each other, that kind of thing. So what we're going to do is we're going to learn to go both directions. So first of all, I'm going to give you the logarithm, which I know its inverse is an exponential. So I want to write it as an exponential. So basically you want to write it as some base raised to some power. Okay, that's what we want to have happen. And that's going to equal, well, on this question, it's a question mark. So let me erase that. Getting ahead of myself. Let me come over here and put it over here. Instead of a question mark, let's do the box. Okay. So basically what we're trying to figure out, we're going to rewrite this as an exponential. So you're always going to start with the base. Here's the base. 2, always go to what it's equal to. 2 to what power, and then equals the argument. Here's the 8's the argument. So 2 raised to what power is 8? The answer is 3. So the answer to that question is 3. Okay, let's try it again. So I'm going to rewrite it because I want to know what this equals, log base 3 of square root of 3, and I don't know what that is because I don't know what log base 3 of square root of 3 is. We will learn later on. We can do that on our calculator, but we could do this as an exponential. We could learn to rewrite it using a base and a power. So we always start with the base. Here's the base. So 3, then you go to the power. 3 raised to what equals square root of 3? Well, if square root is the power of 1/2, then 3 to the 1/2 is what gives me square root of 3. So the answer is 1/2. So the answer to this is 1/2. Okay, question number, or letter C. I want to know 5 log base 5 of 1/25 equals what? Well, log base 5 is not something I know, but I'm going to do its inverse. I'm going to rewrite it as an exponential. So I'm going to say 5 raised to what power is 1/25. Well, I know 5 squared is 25, so then that must mean that 5 to the -2 power would be 1/25. So the answer is -2. Down here, the next one, Log base 4 of 1, well, I don't know any logarithms off the top of my head, but I do know some things with powers. So I'm going to start with the base. Always start with the base. 4 raised to what power equals 1? Well, anything raised to the 0 power is 1. So the answer there is 0. And then the last one, we're going to start here with our base 7. So 7 raised to what power gives me 7? Well, that would be 1. 7 to the 1 power is 7. Okay, so we should be able to take something and go from log form to exponential form and vice versa, from exponential form to log form. So why does all this work? We've got all these properties down here of logarithms. So two things you need to know. Common log is base 10. So when you see something written log x and you're thinking, well, what's the base? I don't know. There's supposed to be a base right there. Okay, if I don't write it and I use the word log, then it's a 10. Down below here, when I write y equals, now this is not 1n, this is an ln. This stands for natural log, and on your calculator, you should have an ln button. That's natural log. So once again, when you're looking at it and you're thinking, well, what's the base? Because I'm using the abbreviation for natural log, the base is e. I don't have to write it. If I write ln, it's understood the base is e. Just like if I write the word log without a number, then it's understood to be a 10. And then down below here, if you use our whole rules that we just did about rewriting, notice if I start here, base b raised to the 0 power equals 1. B raised to the 0 power equals 1. Right here, b raised to the 1 power equals b. B raised to the 1 power equals b. Right here, we start here, b raised to the y equals the power, b to the y. B to the y equals b to the y. Here, this one is written in exponential form, so we would go the other direction. This one right here is written in exponential form, not log form. So you would say, to write it as exponential, you'd start with your base, which is b, and to rewrite it as a log, you would say log base b of, and you come over here to x, equals the power, log base b of x, and that's what you get. So it's because they're inverses of each other and you're just rewriting all of these statements are true. Log base b of x equals log base b of x. That's all true. So if you wanted to look at these and you just wanted to, if you couldn't remember, I don't usually remember those rules that we just went over. I just usually do the work and it usually falls out just fine. So this one, we did have the rule here. What is that base? That's a 10. So I would say 10 to the third power. I always start with the base, then I go to the power, and then I go to the argument. So 10 to the third equals x. So x is 1,000. Here, start with your base. 2, move to your power to the fifth equals the argument. So x is 32. Here, what is my base? It's an e. It's natural log. So I'm going to say e to the fourth, go to my power, and then I end with the argument equals x. And I'm just going to leave that e to the fourth instead of figuring out what the decimal is. I could type it in my calculator and get it as a decimal, but I'll just leave it like that. Okay, so this one says evaluate the given logarithm given the value of x without a calculator. Okay, so what are we trying to figure out? We're trying to figure out what, if I tell you x is 5, that goes right here, and we're trying to figure this answer out right here. We don't know what that is. Log 25 base 25 of 5. That's what I know. Okay, well, I can't use a calculator to do logs, and I don't have them memorized in my head, so the only other thing I can do is rewrite it as an exponential. So I'm going to start with the base. Always start with a base. 25 raised to what power equals the argument. It always equals the argument. So 25 raised to what gives me 5? Well, I think that would be a half. The square root of 25 is 5. So the answer to this question right here, f of x equals log base 25 of 5 is a half. All of that equals a half. If we had our calculators and we could type it in, our calculator would give us a half. Okay, over here on the right, it says log base b of x, and they want me to put x as the square root of b. So this is what we've got. Log base b of square root of b. So you could use the rules, the property rules that we used before. We could do those. We could just do a rewrite, and then you don't have to remember any rules. Always start with the base. So b, start with the base, move to the power, and it always equals the argument. Okay, so what would that have to be? That also would be a half. So the answer here would be a half. Log, let's rewrite that. So f of x equals log base b of the square root of b, and all of that turns out to be a half. You couldn't do that one on your calculator even if you wanted to, because we don't know what b is. So it's kind of good to understand how to rewrite from logarithm form into exponential form. So down here, this says use the properties of logarithms to simplify the expression. Okay, so we could use those properties, or we could just use what we know about rewriting. The answer is 2, but let's see how that works. Always start with the base. Pi raised to what gives me the argument. Here's the argument. Pi over 2. Well, if they both have a base of pi, then 2 has to go in the box. So the answer is 2. So the one on the right, the answer, if we were going to use the properties from the slide before, the answer would be 3. But if we just want to go ahead and not worry about the properties and just remember how to rewrite, we certainly can do that. We would start with the base, always start with the base, 5, raised to what power equals log base 5 of 3. That's our power. Did I do that one right? Log base, oh wait, sorry, back up. That's not a logarithm. Sorry, that's totally wrong. We got to go the other way. This one, okay, sorry, I wasn't paying attention. So used to doing logarithms here. This one was written in log form. So we wrote it in exponential form. So I should have highlighted that. You better make sure you know what form you're in first. And that's probably a pretty common error. And I just made that. So make sure you identify what form you're in. This is in exponential form. So we want to rewrite that into log form. Okay. Okay, so over here is the unknown. That's why I put the box in there so I know what I'm working with. So if we're going to write this in log form, I'm going to start out with the word log. Always find your base. So base is 5. So log base 5 of, don't know what that is, equals, we always go to the power here. So log base 5 of 3. Okay, compare. This log matches that log, that 5 matches that 5, so that must mean then that the answer is 3. And you could do that with the property rules. Anytime this base right here is the same as this base, the answer is always this argument right here, 3. That's what those rules over there on the other side said. On the other slide, the 2 previous slides. Okay, so this one says we're going to use the one-to-one property to solve the equation for x. So basically, we're going to do what we kind of just did on that previous slide. We're going to match everything up. This log matches with that log. This base matches with this base. So the only thing that's different is this argument is different than this argument. So since that's one-to-one, we're just going to say x minus 3 equals 9, and then solve it for x. X equals 12. So same thing over here. This says log. Now remember, that's a base 10, and we don't have to write that. I'm just showing you to help you remember. Remember, if you don't see it, it's a base 10. That log is the same as that log. They're both the same base. So all we have to do is worry about the argument. X squared plus 6x equals 27. Okay, you want it's quadratic, so to solve it, you're going to say x squared plus 6x minus 27 equals 0. Factor that, and you get x plus 9 and x subtract 3 equals 0. So x equals negative 9 and x equals positive 3. Okay, one of these answers doesn't work. This whole negative 9 doesn't work. If you put negative, oh, actually it might work. Let me backtrack that. Sorry. We don't want to have a negative number when we put it back in for our logarithm. So let's just double check here to make sure that it works. So if you put negative 9 in here for x, so negative 9 squared is 81. And then 6 times 9 and negative 9 is negative 73. So that is a positive number. Is 81 minus 70, or yeah, minus 73. What do we get with that? Sorry, it's 63. I didn't mean to write 73. 9 times 6 is, where am I at? 9 times 6 is not 73. 9 times 6 is 54. Yeah, I don't know where that number came from. Sorry. Wasn't paying attention. So this is a negative 54. So now when you do 81 minus 54, that turns out to be 27, and that matches the right-hand side. So that actually, that number is okay to have. Okay, do the same thing with 3. Put your 3 in here. 3 squared is 9. And then 3 times 6 is 18. Is 9 plus 18, 27? It is. So yes, that number works. If you take a number and you substitute it back into the original problem and it gives you the logarithm of a negative number, then you have to throw it out. So just because it's negative doesn't mean it works, but if you plug it back in and the statement's not true or you get the logarithm of a negative number, you have to throw that answer out. Okay, so this one, quick graphing here. It says find the domain, x-intercept, and vertical asymptotes of the logarithmic function and sketch its graph. Okay, so if you remember, the logarithm function had the basic generic logarithm function, had a vertical asymptote that was the y-axis, and a key point here at 1, 0, and it kind of made that shape. All right, so you got to remember that if you want to do transformations. So this one right here, the way it's written, it looks like to me this is moving right 1 and up 4. So what I know about the graph, I'm going to move what I know right 1 up 4. So if I take this asymptote and I move it right 1 and up 4, this new asymptote will be right here, right 1 up 4. Okay, now I'm going to take my key point right here and I'm going to move it right 1 and up 4. 1, 2, 3, 4. Okay. And we're going to have a sketch here. It says make a sketch. So I'm going to sketch this. I'll do blue. So it's going to look like this. It's going to be coming like that. All right. It says to make a sketch. We could type that in our calculator to get more of the exact answers. Some of you are probably thinking, what does the 5 do right here, that base? That 5 just determines how quickly it increases. So whether it kind of goes like this or whether it goes like this, depending upon the number for your base, that kind of changes that shape there of how fast the increase is on the right. Okay, so there's a sketch of it. The blue one's our sketch. So this is y equals, that's a sketch, log base 5 of x minus 1 plus 4. It's not exact, it's a sketch, it said sketch it. Okay, so find the domain. So the domain to me looks like it's everything to the right of 1. I don't get to include 1 because that's my asymptote. So x is greater than 1, or you could put it in parentheses and do interval notation, 1 to infinity. The x-intercept, is where it equals, where it crosses the x-axis, right? We're going to come back to that one for just a minute. Vertical asymptote, we already have that one drawn in, so that's x equals positive 1. Okay, let's do the x-intercept. So if we're looking for the x-intercept, then that means it has to equal 0. So I'm going to say 0 equals log base 5 of x minus 1 plus 4. Okay, I'm going to move the 4 over here. Log base 5 of x minus 1. Okay, so this is in a logarithm form. I can't really figure out the answer, so the only other thing I know how to do is rewrite it as an exponential. So start with your base, 5 raised to the power, and it equals the argument. Okay, so I'm going to say, so my x-intercept is going to equal, I'm going to add 1 to the other side, so x equals 5 to the negative 4 plus 1. All right, let's see what that number is. 5 raised to the negative 4 power plus 1. And that is about, so the x-intercept is 1.00160. So it's just past my asymptote. So I guess I could have drawn it just a little bit closer there. Okay. Okay, let's try it again. So find the domain and the x-intercept and the vertical asymptotes of the logarithmic function and sketch its graph. So it looks like to me that there is no left and right translating. First of all, I see this right here and I see this negative sign. So that too means that it's a horizontal shrink by a half, and that negative is going to reflect it. Now remember, you got to always keep in mind, what does the normal logarithm graph look like? This is what it normally looks like. Okay, you have to know that. So what does that negative sign do to the graph? This negative sign reflects it this way. So I know my picture's got to look something like that, the green graph that I've drawn there. And the 2 is our horizontal shrink by a half, so that's just making it so that it left and right, it doesn't increase as fast. Okay, so how are we going to draw that in? Well, it's a base 10. So normally the logarithm function crosses this point right here at 1, 0. But since we have this negative, do you think that horizontal shrink is going to do anything to that point 1, 0? Is it going to really cross at 1, 0, or is it going to move it somewhere else? Well, if we want to make sure, we can always pick 1 and see what we get when we put in for 1. Or we could even, we could put 0 in if we wanted to see that x-intercept. Maybe we should just put 0 in for y and go from there. Our vertical asymptote is not going to change, okay? And I know that it's supposed to reflect over here. My question is, it's going to look something like this, okay? My question is it really at 1? Is it at a half? Is it at 2? Does that point right there change? So let's figure out what the x-intercept is. Let's put this equal to 0. So if we're putting it equal to 0, remember this is log base 10, even though it's not written because I've used the word log, I know the base is 10. And I'm thinking that 2 to me is a horizontal shrink by a half. So I actually really think the point is going to be right here, over here at a half. But let's see what happens. So it's in a log form. The only way to solve that is to rewrite it as an exponential. So we're going to start with the base. The base is 10. 10 raised to what power equals the argument? Well, 10 to the 0 power is 1. And if you divide by negative 2, x equals a negative a half. So, yep, my thought process was right. It really is shrinking by a half, so my x-intercept, that key point, is going to be at a negative a half, 0. So let's put that right there, and then we'll just resketch that graph in. Something like that. And you could go to your graphing calculator and type that in if you wanted to match it up more accurately. If you wanted to get a point here on the left somewhere, all you'd have to do if you wanted to figure out, well, where is that, how is that shape really turning out to be? So let's say 1, 2, 3, 4, 5. Let's say we wanted to figure out negative 5. Well, if x is negative 5 and we want to figure out what the y value is, this is what we would do. So if I wanted to check this negative 5, 1, 2, 3, 4, 5, I'm going to put negative 5 in for x. So I'm going to say y equals log. This is a base 10. I'm going to write it. You don't have to. Negative 2 times negative 5. So y equals log base 10 of 10. So we're really trying to figure out the y value when it was negative 5, right? So this is our unknown here. This is our box. That's what we were trying to figure out. So if you rewrite it, or if you know, anytime you have 10 to the 10, anytime this base and this argument match, it's 1. It's always going to be 1. So, but you can prove that with a rewrite. Start with your base, 10, and then you come over here to what power equals 10. Well, it's a 1. So at 1, 2, 3, 4, 5, I really should be right there. So my graph should really be even less steep than how I drew it. It should be more like that. Okay. So if you wanted to get a couple of points to make your graph a little more accurate, you could do that. Or you could just look on your graphing calculator. But it's important, guys, remember, you have to have your vertical asymptote in the right spot. You have to have this key point right here in the right spot, and then you got to have your graph facing the correct way and the right shape and that kind of stuff for your sketch. Okay, so here we go. It says, oh, did we finish this one over here? Find the domain. We found the domain. Domain is going to be from negative infinity to 0. And we found the x-intercept. We knew that was at a negative a half. And our vertical asymptote was x equals 0. And then we made a sketch. Okay, this one right here, find the domain, the x-intercept, and the vertical asymptote of the logarithmic function and sketch its graph. So before I start, even though this says natural log, it still has the same basic shape. It crosses right here at 1, 0. It kind of does this. And then we do our transformations to change it. So now you have to look at it and see what's happening here. Well, inside here, 3 minus x makes me think that I'm going right 3. And this negative is grouped with that x, so that makes me think that I am reflecting in the y-axis. Okay, and I don't think my asymptotes, let's see, oh yeah, my asymptotes are going to move because I'm moving right 3. So here's my asymptote, so I'm going to move that right 3. So right 3. And then I'm going to be reflecting. And so this point right here is going to end up, it should end up right here. Okay. And then our graph is going to look something like this. Okay, well, let's just, that was just a sketch there that I made. So I know that my asymptote goes right 3, so I'll come over here and move it right 3. Your key point is always 1 away from your asymptote, unless you've got some horizontal shrinking and stretching going on, and we don't. So we should be 1 point away. And I know that it's going to face the other direction because it's a negative. So this is my key point right here. So let me count that out just so you can see what happens. So normally, right here is the normal key point, but if I move it right 3, 1, 2, 3, and then I reflect it, oops, I got off one, just a minute. So our original, like I was saying, our original point was right here, and then if we reflect it, it would go to here, and then if we move it 3 to the right, 1, 2, 3, we end up right here. So that's kind of how you do that transformation manually. So reflect and then do your left and right movements for after that. And then your sketch, we had the sketch right, so we just sketch that in. You could type it in your calculator, go to your table and see if you had any key points that would be easy to graph. You could do that. It looks like it's kind of a flat graph. So this is coming along like here like this. And then closer to our asymptote right there. So there's our sketch. Okay, so find the domain. So our domain is from -infinity to 3. That was our asymptote. The x-intercept, we could count that one out, is 2, 0. And the vertical asymptote is at x equals 3. Okay, we're done.